to introduce the speaker today. So the speaker today is Professor Graham de Ruiter. So Graham was born in 1985 in Esgravendeel, a small village in the southwest of the Netherlands. I hope I pronounced well the name, but if not, I'm sorry, Graham.
It's a strong chat.
I cannot tell it. He attended Leiden University, where he received his bachelor and master's degree cum laude under the supervision of Professor Jan Reddick. Part of his master's research was performed at the Weizmann Institute of Science here in Israel, where he investigated the self-assembly of metal complexes on oxide surfaces for detecting harmful small molecules. In 2008, Graham returned to the Weizmann Institute of Science to pursue his PhD studies with Professor Milko van der Boom, working on sequence-dependent assembly strategies and molecular logic. After obtaining his PhD, Graham moved to Caltech, where he did his postdoc with Professor Theodore Agapi on the synthesis of multimetallic complexes for small molecule activation and oxygen atom transfer reaction. During his studies, Graham has received the Israel Chemical Society Award for Excellent Graduate Students in 2011, the International Precious Metal Institute Sabine Bella Corporation Student Award in 2013, the Feinberg Graduate School Fellowship, and the Dimitri N. Kras Prize in 2013, and the Azrieli Fellowship in 2017. So now Graham returned to Israel in 2017 as a Horef Fellow to start his independent career, that's here at the Technion Israel Institute of Technology, and now he is an assistant professor at the Schulich Faculty of Chemistry. And I'm very happy that today he is presenting his talk on noble metal-like catalysis with earth-abundant metals. So Graham, the floor is all yours.
Thank you, Morris, for this introduction, and also Simon for this opportunity for me to speak in this virtual EuroTech Alliance lecture series. Indeed, as Morris already pointed out, I started at the Technion my independent career in 2017. So actually in the next 45 minutes or so, I will mainly show you the type of chemistry we've been doing in the first 3 years or so. In particular, in the start, a little bit of chemistry that didn't work out that great, and then we'll show you actually how one carbon atom can actually make all the difference between a good and a mediocre catalyst. So with that, I first would like to share actually the type of research that we are doing in my laboratory. I have a small group, and part of that group is working on molecular materials and self-assembly. In particular, we investigate the self-assembly on 2D materials such as graphene and molybdenum disulfide. And we recently published a series of papers in ACS Applied Materials and Interfaces demonstrating how the isomerization of azobenzene can actually be useful to modulate the optoelectronic properties of both graphene and of molybdenum disulfide. However, the larger part of my group is actually working on transition metal catalysis. A small section is actually asymmetric carbene catalysis, where we use these Diporido annelated carbines of iridium and rhodium to facilitate asymmetric transformations. And these are some of my early work we published in Organometallics. Recently, we have been shifting our attention to earth-abundant catalysis, and this is actually the majority of the work that we're working on now. And this is also the section where I will be talking about today. What they have in common, of course, is that we try to develop new materials and traditional metal-based catalysis with molecular design. So having said that, I will now continue mainly about the earth-abundant metal catalysis. So first, I would like to devote a slide or so explaining why, what, and why we're using catalysis. So the general principles is that if you have a reactant and you want to go to a product, there is typically never a straight line that leads to immediate formation. In general, you need to cross a energy barrier that is shown here in this figure. And this energy barrier here is defined as delta E. So you need a specific amount of energy to overcome the barrier to convert reactants to products. Now, what a catalyst is doing, it actually might stabilize the transition state and therefore lower the energy barrier, making the process overall go faster and at milder conditions. Nonetheless, this is not the only role a catalyst can play. It can also influence product selectivity. For instance, instead of going to the thermodynamic most stable product, you might also switch to the kinetic product or switch the thermodynamic preference altogether. Typically in the industry and in the academia, the most commonly used homogeneous catalysts are still based on ruthenium, rhodium, palladium, osmium, iridium, and platinum, or the group of the precious metals. Now, although these catalysts are very robust and show extraordinary chemistry during the past, I would say 60, 70 years or so, however, with the ongoing drive to provide a more sustainable footprint, we have to also look critically at those catalysts. For instance, from the environmental point of view, the harvesting and purification of these metals from ore actually produces large CO2 emissions. Steel, for instance, or iron has a very large carbon footprint and could benefit from a variety of improvements. Besides that, the precious metals typically suffer from very limited deposits, typically lower than 0.001 milligram per kilo, meaning is that you have to mine a gigantic amounts of ore in order to actually extract suitable amounts of metal that can be used as a catalyst. And typically, most of these metals are quite toxic when they're released from the environment. And this can also be shown that their levels are constricted to the ppm level when they want to be used as administers on drugs. Nonetheless, they also have an economical footprint. For instance, if one has looked at the rhodium price during the past year or so, it has almost been quadrupled, paying more than $10,000 per several grams. So they're very expensive. Again, this is tied to very limited deposits and also brings us into issues of the long-term supply. What do I mean with that? Is if one looks at the mining of essential metal-containing minerals, you can see that the total production from 2017 mainly originated from Asia, so more than 55% originated from Asia, and Europe and North America in particularly only contribute about 20% or so. Nonetheless, if one analyzes the total production in terms of political stability, one sees that in general, almost 65% comes from politically unstable or extremely unstable countries. And that actually puts a large pressure on countries such as in Europe that do not have their own natural resources to produce these precious metals and therefore are reliant on foreign sources. So there are a lot of incentives actually to change these types of catalysts, not only for an environmental point of view, but also from a sustainable point of view as well. Therefore, when I started my independent career, and I'm not the first one to do that either, is I started to look at first strong transition metals. So if one look at this screen, so here one can see the abundance of elements per 10 to the 6 or per million atoms of silicon versus their metal price. One thing that immediately stands out that iron and manganese are quite cheap and very abundant. Besides that, also aluminum and sodium and calcium are quite abundant and relatively cheap. It's also not surprising that one sees in the literature an increasing amount of catalysis based on aluminum and also some calcium. For instance, some calcium N2 compounds have recently been reported as well by Schulich Hydrides. So generally, these earth-abundant metals, of course, they are environmentally friendly. They are abundant and generally geopolitical favorable, meaning is that iron and manganese typically can be found all over the world. And besides that, they are very, very cheap. if one can see, for instance, the price of 1,000 kilograms of iron, so 1 ton of iron typically is about $600, which is a very good source if one can use that. There are also some disadvantages, however. For instance, is that typically these earth-abundant metals, they're oxophilic, so they really like oxygen. And generally, it's not that simple to control their 1 electron versus 2 electron chemistry. Besides that, generally, they also contain multiple spin states. So in general, controlling their reactivity is not that straightforward. One can see that here also in this graph here below. One looks at the unique properties of earth-abundant metals. You can see here, for instance, here in this octahedral field, that if you go on from the first to the second and third row, that the energy difference between the d orbitals generally increases, meaning that for the second and third row, you will most likely encounter low spin compounds, while for the first row transition metals, you might also encounter high spin. And this orbital splitting actually leads to very different types of unique reactivity patterns that, if harnessed properly, can be beneficial. On the other hand, generally, earth-abundant metal complexes also result in weaker metal-ligand bonding. As you can see here, so here you can see the kinetics of water exchange on aqua complexes. And you can see that typically most of the earth-abundant metals, except here for palladium-2, exhibit very fast exchange on the metal center. So it's not that easy to bind a substrate and perform chemical relevant transformations. Well, typically it's more easy on the later transition metals of the second and third row. However, I believe, and I'm not the only one, that many of these properties of the earth-abundant metals can be harnessed if one actually uses a proper metal ligand design. So, of course, in order to try to figure out and deduce what is actually a good ligand type of design, nature provides us most of the time with an inexhaustible source of inspiration. So here I've shown on this slide some anaerobic gas processing enzymes in the form of hydrogenase and dehydrogenase. So if one looks, for instance, hydrogenases typically have different compositions, all consisting of earth-abundant metals, either iron, iron-nickel, or iron-iron combinations that show very high rates of hydrogen formations up to 10,000 molecules of hydrogen per second, which means that if you would have 1 mole of this enzyme, you could fill up the Hindenburg Zeppelin in a matter of hours. Besides that, in the cell, they are used for energy sources. But one thing that is important to realize is that 1, they use earth-abundant metals, but 2, they also might facilitate metal-ligand cooperativity in terms of this amine in close proximity that can protonate any incoming hydride, for instance. C-hydrogenases works very similar. Again, we see the same type of metals, although this time in a different arrangement. So here you can have an open cubane, and here you have metal-metal cooperativity, for instance, to convert CO with water to CO2 to protons and an electron. And this is very similar to the industrial water gas shift reaction, besides that this is occurring under ambient temperatures and pressures. So nature actually uses a lot of earth-abundant metals, and we can already see some aspects of ligand design in terms of metal-ligand cooperativity. Now, in the scientific community, people actually have looked at a variety of different of metal-ligand cooperativity, and I'll highlight a few of them, and some of them I will also use in this talk today. So you have what is called chemical metal ligand cooperativity, and this has been really pioneered by David Milstein, where he uses the aromatization and de-aromatization of the ligand backbone to overall activate HY bonds, for instance. And this process is overall redox neutral and avoids the unwanted 1 electron transport. And the nature of the HY bond could be a variety of processes. This could be alcohols, could be amines, it could be H2, it could be water or ammonia. And this facilitates a wide variety of processes. A different type of chemical of metal ligand cooperativity is electronic. And this has been really explored by Paul Chirek at Princeton. Again, this is an overall redox neutral process with respect to the metal. But in order to avoid the unwanted one-electron processes, you use the ligand backbone to store electrons that then can reversibly be used during chemical transformations. As you can see here in the CC bond cleavage, which is a one-electron process on the metal and a one-electron process on the ligand, overall providing the 2 electrons needed for many organic transformations. And generally, these types of reversals of the electrons, it's typically reversible. Another is metal-metal ligand cooperativity. We've seen this example also already in nature, where you have 2 metals in close proximity that enable to facilitate the activation of a wide variety of small molecules. This is very analogous to kind of Lewis base or frustrated Lewis pair interactions, in which one of the metals acts as a Lewis base and the other one acts as a Lewis acid. Again, this activates a variety of H-Y bonds, for instance, here in the case of H-bipin, and again enables favorable one-electron chemistry. The last part that I want to talk about is one can also use strong field ligands. This actually forces a low spin electronic configuration, and therefore you can enable 2 electron types of chemistry. And this is more analogous to the traditional noble metal type of reactivity. Nonetheless, it's not entirely necessary, because Pat Holland at Yale uses a different approach that shows that you can also tailor ligands to stabilize high spin intermediates that show very unusual reactivities. And during the course of my talk, I'll also show one example where this is actually happening. Nonetheless, when I started my independent career, I tried to focus on electronic and metal ligand cooperativity, or using strong field ligands. So the first part of the talk is trying to understand the extensive redox non-innocence in earth-abundant metal BP diamine or diimine complexes. And as I mentioned, so redox non-innocence is already a relatively old concept, first already observed and pioneered by Harry Gray in the early 60s, who realized and saw that these metal diethylene complexes are far from innocent. So when you do the reversible one-electron transfer, either if you want to put an electron, you want to take out an electron, most of these transformations are actually ligand-based. Then in the late 2000s, these types of reactivities were invested by Wiechard at Max Planck Institute on these pyridine diimine complexes. And what they show is that upon reduction, for instance, or upon metallation, there is significant radical character action on the imine part of the ligand. And this, as you can see from their cyclophotellograms, is relatively reversible. So most of the ligand, or most of the one-electron transfer processes are actually ligand-based, except here for cobalt at very negative potentials. This is a metal-based type of reduction. Later on, of course, this was exploited not only by Paul Chiric, who shows that these iron alpha diamine complexes are extremely active for some hydrocellulation and polymerization reactions, but also by the beautiful chemistry by Chris Ueda at UPenn, who shows some really amazing transformations by utilizing this one electron transfer from the ligand. So when I started, I thought it would be a good idea to try some of these ligands, particularly on a bipyridine scaffold. The reason is that BP compounds typically bind very strongly to earth-abundant metals with a rigid redox inactive backbone. But if we introduce, let's say, redox non-innocent functionalities, such as these imines here, perhaps we can facilitate multi-electron transfer processes beyond typically what we see in the literature. Now, these compounds have been investigated already by Solan, who showed here, for instance, this nickel dibromide compound. But what he noticed that there was a lot of structural flexibility, and therefore they were never really further investigated after 2009. So we decided to synthesize these ligands with mesotose substitutions here on the imine. The synthesis is relatively straightforward from the dibromo-pyridine, and actually we can make these ligands on multi-gram scale. And as you can see on the next slide, The methylation step is relatively straightforward. It's just using a metal triflate salt in acetonitrile, and it will afford a variety of different compounds based on manganese, iron, and here you can also see cobalt. Yields are typically between 65 and 90%, although it's very important that actually one synthesizes the metal triflate salt from the corresponding metal to avoid any unwanted chloride impurities that you get if you buy it commercially. Nonetheless, all these compounds are isostructural, except here for manganese, which is pentagonal bipyramidal, which happens if the compounds are dissolved in acetonitrile, where you can have actual ligation of the acetonitrile molecule, but this ligation is reversible depending on the solvent. So typically they're octahedral with two actual coordinated triflates. So with these compounds in hand, we actually investigated their electrochemistry in the glove box, and we were very happy to see they exhibit very beautiful cyclic voltammetograms. So for instance, here for iron, you can see when we scan in the negative mode, we see two reversible reductions in close proximity, and finally by a reduction around -2. We also observe an oxidation wave. We think that's an oxidation from iron 2 to iron 3. Analogous to iron, we also see a very similar CV for cobalt, except for the fact that the reduction waves are a bit further separated from one another, which actually facilitates their isolation. The question then arises is whether these reduction processes are ligand or metal based. So besides the multifaceted redox non-innocence, we really want to know what is the electronic structure of the metal center, what is the spin state, are all these one electron reductions ligand based, and actually can we use these reversible electron transfers for organic transformations, and if yes, can we observe also some reactivity differences depending on the metal center? So to answer these questions, we embarked on a spectroscopic study that lasted at least 2 years, and I kind of regret afterwards actually going into the subject because it's quite challenging to figure out exactly what's going on, but I think we've cracked it now. So you can perform a 1 electron reduction with sodium amalgam in THF, and what we suspected was that we would form a ligand-based radical. So what we actually did is we compared the bond distances, the experimental and the calculated ones. So one would expect that if one actually forms a radical, that the C10 to the C10 and the A1, actually that bond distances would elongate, while the C12 and the C10 actually would contract a little bit more. And this is exactly what we see. So for instance, if you look at the N1 C10, you see that upon the reduction, this bond distance actually elongates from 1.27 to 1.32 angstrom. Likewise, the C10, C12 distances actually shortens from 1.49 to 1.41. So, and this is exactly also what we get, of course. These are all from the crystal structure. So the solid state structure actually indicates that there is indeed a radical present with significant character on the ligand backbone. We also observe this by EPR spectroscopy, where we can see a nice signal corresponding to the ligand radical, and by EPR transmutation experiments, we know that the overall spin state of these systems is S equals a half. So this is a doublet. This also makes sense based on our Mossbauer spectroscopy. So here you can see our signal. We have actually 2 species present. The majority here, one shown in blue, has an isomer shift of 0.3 millimeters and a quadruple splitting of 1.16. And this is very indicative of an iron intermediate spin iron S equals 1 metal center. So it means that we are 2 unpaired electrons on the metal, which is antiferrometrically coupled to the one on the ligand, giving overall a doublet spin state. And this is actually also what we found by broken symmetry calculations, which we're actually finalizing right now. The question then arises, what happens actually when you take this compound and you reduce it for a second time? So Similar, we were able to crystallize this compound. So here we see a square pyramidal compound with an actually coordinated acetonitrile molecule. And you can see even further that again, upon reduction, the bond distances even further elongates for the N1 to C10 to 1.35. And again, we see a quite strong reduction of the C10, C12 bond distance. The Mossbauer parameters now shows a clean species, again, indicative of an iron 2 intermediate spin S equals 1. So this means that this compound with 2 radicals on the ligand is actually a singlet state where both of the radicals couple to the 2 unpaired electrons on iron. And this is again something that we also get from our computational studies. So far we know that if we do a 1 and then another electron reduction, that both of the electrons are actually going to the ligand. So the other question then becomes, is that what happens when we reduce it for a third time? Where is this third electron going? Is it again going to the ligand, or is it now going to the metal? So fortunately enough, we were able to isolate and crystallize this, this metal center. In this case, it's a square planar iron. And from the bond distances, it appears to be that the electron is actually going to the ligand. One would appreciate if one looks at the N1 C10, C10 C12, and N2 C12, basically this part here, that more or less all the bond distances are almost becoming equal. So that might indicate that there's a strong delocalization of the electrons here in this part of the bond, very similar to what we saw with the dithiolene compounds. However, our Mossbauer spectroscopy was not clear. It shows actually 2 peaks more or less equal integration, so it's a 50-50 mixture. One indicates a intermediate spin iron S equals 1, and that would indicate that the ligand, or that the radical is actually going to the ligand, forming a trianionic ligand with partial deamerization of the ligand backbone. Nonetheless, there is also a species with an isomer shift of about minus 0.12, and that actually indicates that there is some significant iron 1 character present. And although computational studies indicate that the electron prefers to go to the ligand, our experimental studies show that it might not actually be such a simple description, and that actually it might be a combination of both. So there is and significant radical character on the ligand, as well as some iron 1 character as well. Nonetheless, it really shows that these compounds, now that we have isolated, really show some multifaceted electron chemistry, where the majority of the electrochemical transformations of the electrons that we put into the system are actually located on the ligand, and ultimately almost resulting in a delocalization and deamortization of the ligand backbone. We're currently finalizing the electronic and magnetic properties to give the definite assignment of the spin state, but for now, as we expect for iron, for an iron 2, so this is a quintet indicating 4 unpaired electrons on iron, and these are overall doublet. This is a singlet, and the final compound again is a doublet, meaning there are 2 unpaired electrons on the ligand, antiferromagnetically coupled to a single radical on the ligand as well. So with these, with the electronic structure established of these compounds, we really wanted to know whether we can actually exploit them in a variety of transformations. And we tried to focus on the hydrocellulation and the hydroboration of alkenes, not only because they are important for commodity chemicals, but also in the fine chemical industry. Especially our attention now, and in this lecture, I will focus on a nice study we performed on the hydroboration. But in the end of the day, I will also show to you actually why we didn't continue with this research direction. And nonetheless, when we started to investigate these cobalt complexes, we quickly found out that if we use our cobalt catalyst, in this case substituted with isopropyls on the imines, that in the presence of HB-pin and sodium terpetoxide, we can actually hydroborate a variety of alkenes, not only terminal ones, but also internal ones. So you can see that 1 octene to 4 octene typically gives the linear anti-Markovnikov hydroboration product and fairly good yields, depending on how far the isomerization needs to happen. So typically, for the further away the alkene is located from the terminus, the lower the yields become. The functional group tolerability typically here is limited to aliphatic alkenes, but generally the yields are quite high, regardless of the stereochemistry of the alkene, whether it's E or Z. The only reason also here that I show you this is for allyl benzenes. Typically, we get a variety of mixtures between alpha, beta, substituted hydroboration products, which is not the case for manganese. Actually, what we found is that there is a quite strong metal-dependent divergence, meaning is that if we use cobalt, we see remote hydrofunctionalization of internal alkenes. However, if we use manganese, we see terminal alkenes only with a strong anti-Markov-Markov selectivity. So the question now is, can we actually determine the mechanism of hydroboration, and can we determine the origin of the metal-dependent selectivity? So in order to do that, we collaborated with a computational group in Australia, and we looked at this process computationally. And we evaluated the transformation on a variety of spin states. So we evaluated single, triplet, and quintet spin state, depending on how the radical couples to the metal, and whether or not the metal's in the low spin or high spin configuration. So generally, what is well established is that these compounds form some kind of metal hydride intermediate, followed by alkene coordination, insertion, followed either by oxidative addition of the HB pin and reductive elimination, or direct sigma bond metathesis. So when we started the evaluation, first we looked at the overall stability of the hydride, and we found that for cobalt, the singlet spin state is the lowest one in energy when all the arms of the ligand are coordinated. For manganese, it's the quintet spin state that is lowest in energy. However, if one wants to decoordinate one of the ligands, as you can also see here in the optimized structures, typically this is an uphill process of about 25 kcals per mole for cobalt and about 13 kcals per mole for manganese. So when we first started, of course, we looked at cobalt, at the cobalt process, and in particular, first with the alkene insertion and whether or not this is feasible. And indeed, what we show, and here you can only see the singlet versus the triplet, that alkene insertion is actually feasible on the singlet potential energy surface. So when we start, of course, we need to decoordinate one of the ligand side arms in order to make a space for the incoming ligand, which is typically uphill of about 25 kcals per mole. After going through this intermediate, where we have the coordination, the transition state shows for actually alkene insertion is much lower on the triplets on the triplet surface than it's on this. Excuse me, it's lower on the singlet surface than it's on the triplet by about 10 kcals per mole. After the insertion, we create the internal alkyl process, which is then followed by, again, beta hydride elimination, rotation, and then again, insertion to give the final terminal alkyl species. What you can see is that there is virtually no difference between the internal alkyl and the terminal alkyl species, which means that we have a Curtin-Hammett type of scenario where the type of selectivity actually depends on the final borylation step. What is also obvious is that, again, if we have coordination at one of those intermediate stages, it's very energetically downhill and could provide a trap for our catalysis. And we know that typically we need very high temperatures and/or catalyst loadings in order to facilitate these transformations. If one looks actually at the type of borylation, there are very little differences between the internal and the terminal borylation of the alkenes. What we do find is actually that regardless whether it's internal or terminal, that the borylation is actually favored on the triplet surface, So here you can see a calculated barrier of 28.5 kcals per mole, and here you can see a barrier of 27.9. So here, quantitatively, we show that actually the terminal correlation is more favorable on with cobalt, although the insertion of both terminal and internal alkenes is feasible. I would also like to highlight the differences between the two, because for internal borylation, it appears that actually oxidative addition of the borane is favored, while for terminal borylation, we could not isolate such an intermediate computationally, and therefore we actually propose a direct sigma bond metathesis with an overall barrier of 27.9 kcals per mole. So for cobalt, of course, what we found is that internal and terminal olefin hydroboration is allowed. I didn't show you the complete substrate scope, but we have about 20 examples, and we have metal-based selectivity. The question now is that so what's happening with manganese? So for manganese, the story is quite different. The quintet is the lowest state, but regardless whether you're on a triplet or on the quintet potential energy surface, you can see that actually alkene insertion into the metal hydride is actually quite high or too high under experimental conditions, and therefore is not favorably. So terminal alkenes are inaccessible by manganese, although dissociation again of one of the ligand arms is necessary. So this explains for us at least why isomerization is not observed. For terminal alkenes, the barriers are slightly lower, and for borylation, of course, we see a quite low barrier for sigma bond metathesis with an overall barrier of about 20.5 kcals per mole. So overall, what we see is that for cobalt and manganese, insertion of internal alkyls is only possible for cobalt, but not for manganese. Insertion is the rate determining step for manganese, but for cobalt is actually borylation, and the overall transition state barriers for the rate determining step is about 28 kcals per mole for cobalt and 31.5 kcals per mole for manganese. And this also explains some of our differences, that typically for manganese we need higher temperatures in order to achieve complete conversion. So basically our computational studies quantitatively agree with our experiment. So I will quickly skip these. So what we actually saw so far is that the electronic structure studies reveal extensive ligand-based non-innocence that promotes both the hydrosylation and hydroboration of unactivated alkenes, where we also saw a metal-based divergence. Nonetheless, in all of these systems, the reactivity is really lacking compared to Chiric's standard, and many catalysts are able to catalyze hydrofunctionalizations for now on. So because we really didn't see those nice high impact results, we decided actually to switch to a different project, although it's quite related, as I'll show you, and that's related to the formation of PCP pincer complexes of earth-abundant metals. And is this a scientific curiosity or really a catalytic powerhouse? So far, what I've really told you about is modified bipyridine compounds, whether or not with redox active ligands. And I realized is that perhaps what happens if we would transform this into a carbene. So if you add one carbon atom exactly here in the middle, now you have the potential to generate a carbene here. And if you functionalize the side arms, for instance, with phosphine donors, you really come to a very nice pincer type of geometry. Now, these compounds, for instance, are known as Diporido annihilated carbines. And as you can see, if you can compare them to different types of carbines, is actually they result in quite electron-rich metal centers. So here, the metal center is more electron poor, and the more you go to the left, the more electron-rich they become, depending on which is judged by the CO stretching frequency of the metal carbonyl. So you can see here both that they show very promising stretching frequencies resulting in relatively electron-rich metal centers. The pincer type of motif, of course, is very well known in earth-abundant metal catalysis, and there are at least 15 people, major players in this field, all with a slightly different type of pincer geometry. But generally, they either form an amine or amide, or a pyridine as the central moiety. But if you look at the prevalence of carbene pincer complexes, where the central atom is actually a carbene, it's much less. And to the best of my knowledge, there are only 6 different types of species reported so far, and the majority of them actually belong to the same ligand class. Please note, of course, that the only PCP type of compounds are shown here in the middle. Well, the ones here on the top by Illuch, Warren Pierce, and Rowan Young actually are quite different, because they are more considered achillidine compounds instead of the NHCs that we are using. So about 2 years ago, I became interested in these types of ligands, first reported by Yamamoto et al. About 6 years ago, and they show that actually these type of compounds are quite good for coordination. They're quite good to coordination of late transition metals. There are good sigma donating ligands, resulting in overall electron-rich metal centered in a PC type of ligand type of geometry. The problem is typically they are low-yielding synthesis, and there's no catalytic activity reported. Moreover, the earth-abundant metal complexes are unknown. So basically, these were the last reports in 2015. So I thought that actually they might be good for coordination to earth-abundant metals. So what we did is we optimized the ligand synthesis, so we can now synthesize these again in gram scale. So when we started, we can actually take the carbene. It's not shown here, but this should be a carbene. We take iron dichloride THF product, and we can actually generate the iron dichloride species here, as you can see from its X-ray crystal structure. In this case, the phosphine is substituted with phenyl. It's diphenylphosphine. Upon reduction, however, when we wanted to study the N2 coordination chemistry, actually what we found out is that the ligand is actually non-innocent, and the iron 0 actually coordinates to one of the arrow-phosphine arms, and this compound is relatively stable, so it will not react with electrophiles, and it's kind of a rock, so a little bit stuck in that case. So therefore, we decided to replace the phenyl on phosphine with isopropyl, and lo and behold, now the reduction works much better. So if you now reduce it with 2 equivalents of potassium graphite, you can actually get the N2 compound, although the dinitrogen coordination or the dinitrogen activation is not very strong. However, if you try a different method for reduction and you use sodium triethyl borohydride, now what we found is actually we can generate the iron dihydride compound. And this is unusual because typically in a pincer type of geometry, iron dihydrides, especially in trans geometry, are not known to be stable. And so inadvertently, we actually generated the first stable iron dihydride compound, as you can see here from its crystal structure, that coordinates N2. Now this N2, of course, as we all know, is a weak ligand. So now we have a large possibility to open a variety of different types of chemistry. So again, so this is the first example of an iron complex in a PCP pincer type of geometry, and we also have the trans dihydride. So when we use this strong ligand, can we actually use it for beneficial chemistry? Indeed, we can, because when we actually took this iron dihydride and we dissolved it in benzene, my student Subhash quickly realized is that when I analyze the hydride region, that after about an hour or so, we see a quite strong reduction in the signal at about -0.9 ppm where the hydrides are located. And this is interesting because in 2016, Paul Chiric reported that iron compounds could be used for HD exchange at aromatics. isotope exchange is indeed mediated by an ion complex, and they proposed the involvement of a distinct ion dihydride. Now, because we were able to isolate this ion dihydride, but we did not need an H2 atmosphere, perhaps we could actually do a better type of chemistry. And indeed, it works quite beautifully. So you can take a wide variety of aromatic substrates, whether it's aromatic or heteroaromatic. It doesn't really matter. You take 5% more of the catalyst in benzene D6, and what you see is selective HD exchange and a variety of different positions. So we can have toluene, fluorobenzene, chlorobenzene. Note that we do not see any oxidative addition of the iron-chlorine bond. Esters, amines, and amides are tolerated quite well as a wide variety of heteroaromatics. The HD exchange typically occurs quite well with more or less 90% or more deuterium incorporation. The only one that's not really working is this ketone, and I will get to that in a moment, and we also know why this is not working. The mechanism of this reaction was investigated computationally and occurs via a metal-assisted sigma bond metathesis. So again, this is an overall redox neutral process. What is important, of course, is the dissociation of the N2 to create a vacant coordination site, and then basically we have the formation, or at least computational constantly suggests we have a sigma complex forming. You can see also from the transition state in this case that the deuteride here, or the hydride, is already important, because you can already see that there is already quite some interaction, which is very reminiscent of the cis effect reported by Eisenstein and Colton. After that, you have cleavage to create this aryl isotopologue of hydrogen, which then can switch around, which puts now the deuterium in close proximity to the metal center. Of course, then the reaction occurs in reverse, and then you get exchange, and the deuterium ends up now on the benzene. Now, this deuteration is also dependent on some steric and electronic factors, which we also investigated it computationally. So here you can see the transition state barriers to CH bond, sigma bond metathesis. And what we found out, of course, if you have benzene, more or less there is no difference between the ortho, meta, and para position. If you substitute it with methyl, so you go to toluene, you see now that due to steric effects, actually the ortho position shows quite a high activation energy or activation barrier with respect to the meta and para position. This is also what we observe with dimethyl amine. Again, the ortho position is now very unfavorable. As well, you see an increase in the para position as well. And we can actually track this by NMR. So if you analyze this by NMR, you see that first the meta position will get deuterated. For methoxybenzene, you can see again that all the positions are relatively have the same energy barrier, and we see that there is no difference in deuteration. While for fluorine, the ortho and meta position are lower, and this is really the result of the distinct ortho fluorine effect, also reported by Bill Jones and Max Perutz earlier in the 70s and 80s. And we can again track this also by fluorine NMR, so we can see that the majority of the HD exchange first occurs ortho, followed by meta and para in close proximity. So the electronics effect that we found is that there is a distinct orthofluorine effect, and pre-coordination enables orthodeuteration as well. So if you have a heteroatom in close proximity, this will also facilitate the HD exchange. Generally, sterically accessible CH bonds are efficiently deuterated. This is also a kinetic effect. While electron donating substitution destabilize the developing negative charge ortho and para position, although typically at the temperatures that we operate the reaction, this is negligible. If you want to know more, these papers and reviews are very beneficial to study the CH activation mediated by iron. I would want to go back a little bit and try to figure out why ketones resulted in absolutely no conversion. And actually, when we checked by NMR, what we found out is that these iron dihydrodes actually react with the ketone. Now, we couldn't really isolate what these species were. So what we tried to then do is see what happens if we actually take the iron zero complex and see what happens, because one can readily envision if you have reductive elimination of H2, you can generate an iron zero compound that perhaps this reacts with the ketone. And this is indeed the case. So if you take the iron zero compound, which we can independently prepare, you add the ketone, is what we see is relatively oxidative addition of the CH bond ortho to the ketone. So resulting in this cis hydride, where you have the cis orientation of the carbon and the hydride next to one another. However, when we used an ester or an amide, we actually found the trans product, where the carbon atom and the hydride are trans. And you can see this clearly from the crystal structures. So we're wondering, how can that be if that both these substituents are direct in group? How can it be that you actually get two different types of products, which can readily be distinguished in the NMR? So one of them has a resonance that's -9 ppm, and the trans product has a resonance at around -23 ppm. So basically what we found out here is also on the next slide, is that the mechanism is actually chelation assisted or non-chelation assisted. So chelation assisted means is that first the heteroatom coordinates to the metal center, which is then followed by CH bond cleavage, which necessarily puts the carbon and the hydrogen cis next to one another. However, if the activation is non-chelated assisted, you'll get oxidative of the CH bond followed by rotation, and then actually you have the carbon and the hydrogen opposite to one another. So this is a result that was also observed first with iridium about 15 years ago, and now we see the exact same thing happening with iron. And what we believe is that this pincer ligand actually facilitates a lot of transformations that are analogous to precious metals. Which is highly favorable, because that's exactly what we're trying to do. We're trying to displace these precious metals for more favorable, such as iron. Nonetheless, I think I have a few minutes left, so I will go to the final few slides of my presentation, where we will discover how we can actually assess the iron hydride chemistry at different oxidation states. So I already talked a little bit about the reactivity of this iron zero, where we saw CH activation of aryl ketones and aryl esters. However, if you use, and this is only specific, this only happens in toluene, if you react this with sodium triethyl borohydride, you can generate this unusual anionic iron hydride dinitrogen compound. And when we isolated this, we quickly realized that there are very few of these compounds reported in the literature. The most well-known ones are these iron tetracarbonyl hydrides that have been known since the early 70s. But since then, really, there has been really no progress, except for one report by Jonas Peters in 2019, who isolated this as an intermediate along the N2 reduction pathway, although they could not isolate or not locate the hydride in the difference map. Now, these iron tetracarbonyl hydrides, they have been established to have a nice type of chemistry, but they're very poor alkene isomerization catalysts. And generally, until 2015, there are very few examples of anionic iron hydrides. Nonetheless, we were able to isolate. So here in the crystal structure, you can see this is actually a dimer, although in solution, we more or less know that this is a monomer. So we could clearly see the hydride N2 compound. And it turns out that this is actually a very efficient alkene isomerization catalyst. So we can isomerase a variety of terminal alkenes to the internal alkenes, and this is specific for one bond isomerization as well. So here you can see the one bond isomerization on the top of allyl benzenes, and they generally result in very high EZ ratios with high yields, and typically catalyst loadings are about 0.1 mol% to 0.5 mol%, depending really on the purity of the reagent, because not everything is as pure as we would like to. We can also do the one bond isomerization of linear alkenes. For instance, you can see here hexene and octene, and we can already see that the catalyst loadings are going down drastically to about 0.05 mole percent. The EZ ratios typically are 10 to 1 or larger, with yields that are quite high. And recently we published this in Catalysis. What is really unusual about these types of compounds is that you're not only limited to one bond alkene isomerization. So here what we did is we show that you can do one bond isomerization if you make the alkyl chain longer, but that you can also do selective multi-bond isomerization if you actually start heating the reaction medium and you increase the catalyst loading. So here you can show that we can do 2-bond, 3-bond, and 4-bond isomerization. Nonetheless, this is not even as low as we can go, but we can also show that if you purify the alkenes, actually our catalyst works with low ppm levels as well. So here you can see this is a gram scale reaction, so this is 12 millimole hexene, 6.2 ppm catalyst loading for 24 hours gives you more than 95% yield of 2-hexene with an E to Z ratio of 10 to 1 and higher. We can do it also for octene or allyl benzenes, although for allyl benzenes we need slightly higher catalyst loadings as well, although EZ ratios of course remain excellent. Isotope labeling studies are fairly conclusive towards an alkene type of mechanism. So we readily see deuterium scrambling across all 3 positions, and also crossover experiments show that an iron hydride is the intermediate, as we see deuterium incorporation on both, or basically we see crossover between allyl benzene and dimethoxy allyl benzene as well. So really this favors an alkyl type mechanism where we have dinitrogen coordination followed by alkene coordination, insertion, followed by rotation, beta-hydride elimination to the alkene, and followed by again alkene exchange. And this process is overall it's exothermic, it's going down, it's basically the delta G of the cycle is minus 3.8 kcals per mole. However, what is most interesting, and I think this will be the last slide before I'll stop, is that the isomerization is actually dependent on the spin state. It is well known that 4-coordinate iron complex can actually have close-lying triplet states. And this is actually see that after the alkene insertion, moreover the triplet state is actually dominating, providing a very low energy pathway along the isomerization manifold. Although the singlet state, of course, is at room temperature of the iron N2 compound is the ground state, but we see that the excited triplet state is actually doing all of the work. And this is actually demonstrating why these compounds are so extremely active at room temperature. Is basically you add your catalyst at low catalyst loading, you go to an NMR, and before you get to the NMR, your reaction is done. So I think with that I will end. So I'll skip the remaining slides of the other types of chemistry we can do. So to summarize, we starting from some redox non-innocent ligand scaffolds, we were able to actually modify the ligand by adding 1 carbon atom and going to an iron PCP pincer complex that shows remarkable reactivity for the hydrogen deuterium exchange of heteroaromatics. We also saw some very efficient alkene isomerization. Unfortunately, I didn't have time too much to talk about the alkyne functionalization, which is Z-selective or some other type of hydrogenation reactions. And nonetheless, these compounds are still being investigated, and we already know that we can do ion catalyzed cross-coupling. We can also do directed CH bond functionalization and some dinitrogen to ammonia conversion, all with a single ligand with iron. And of course, there's much more chemistry to explore. I haven't even talked about the chemistry we can do with cobalt or manganese, which we hope to publish shortly. And nonetheless, all the work that you saw on the PCP pincer complexes have been done by my PhD student, Subhash. The redox non-innocence was mainly done by Ranjish. This is my total group, so I'm very grateful to have such a group of talented students who are really doing all the work in the lab. I also like to thank my collaborators, Gabriel Menar at UCSB, who recorded initial Mossbauer. Now we're working with Michael Neidig at Rochester for spectroscopy regarding iron cross-coupling, and also Amit Karton, Inke Ranan, and Linda for additional support, and of course these funding agencies. I'd like to thank you for your attention, and I would be happy to address any questions. So thank you so much for this opportunity to share a little bit of my research. So thank you all.
Thank you so much, Graham. It was an excellent presentation. I know we are a bit over time, but I think a lot of people are still joining in and sitting in. So if anybody has any questions they want to address to Graham, please raise your hand either virtually or just unmute yourself and ask a question. But very great presentation. And just as a last thing, I want to say that this is our last professor's speech prior to the summer holidays, as we in the EuroTech have some different holidays all over the summer. So this is the last opportunity you have to address one of our professors. Raja has the first question. Please unmute yourself and say the question.
Hey, Graham.
Hey, Raja.
How are you? So,
good. How are you?
Very good, very good. I was very much interested on that dihydride you have on iron dihydride. Were you ever interested to find the pKa of that? Because the why I asked this is when you showed the dihydride, you said the chemical shift was like minus 8.9 or something like that. But then when you reacted with that ketone, then that monohydrate shifted to minus 20 or something. So I was kind of interested to see the pKa values of that.
Yeah, we haven't investigated the pKa values of the iron compounds. I can tell you that the chemical shift that we see is actually depending on what is trans to the hydride, whether it's the carbon or the oxygen atom. So that's mainly responsible for these systems. What we do know, basically, a little bit of empirically, is that they're not that hydridic at all. So it's not that they're very reactive. So it's, but we, to be honest, we haven't really investigated. What I want to do is a computational study into the electronic structure of a variety of hydrides. We don't only have this one, we also have an anionic trihydride, iron 2 species as well. So, but definitely, I think it's very interesting to see what those pKa values will be and how we can actually utilize that chemistry further on.
Because the most startling thing was when it was dihydride, it looks a little bit less reactive. Then after losing the first hydride, it becomes more reactive, the second hydride. So that's why.
Yeah, iron dihydride is not. It's relatively stable. Yeah. So the anionic monohydride is much more. It's much more reactive. The dihydride itself does not do alkene isomerization at all.
Great. Thank you. Thank you.
Perfect, thank you. Any more questions for Graham? Otherwise, I just want to say thank you so much, Graham. The recordings of this and maybe also the slide deck will be published at our homepage, EuroTech.eu. I will forward you other interested news from our side on the other side of the summer holidays. So thank you so much, everybody. And thanks to you, Graham, for ending this speaker session prior to the summer holidays. And I hope that you will enjoy the summer as well when you get to that point.
Thank you so much, and enjoy the summer. It was really a pleasure to give this presentation. So stay safe, everyone, and thanks again for this opportunity.
Thank you. Ciao.
Bye-bye.